Hi, Dr. Elaine. This is Cara. I'm doing a reassessment as a work energy assessment. Here's my original paper. I missed the mark, so I wanted to try again. So my problem that I'm going to use is that a woman's pulling her son by a string attached to a cart. So she's pulling the cart by a string, and the total mass of the cart and the boy is 30 kilograms. And then the string that she's pulling is at a 26-degree angle. And the coefficient of friction, kinetic friction, is 0.16. So I'm going to find the work done by the woman and the work done by the ground on the cart while it's moving 120 meters. I'm also going to give the total work done on the cart at the end. So start with first part here, where I look at the tension force, and that's T in my my free body diagram. So I find the total forces in the x direction, which would be T cosine theta minus the friction force. So the friction force is going to the left there, and then the tension force, we're looking at the x portion of the x component, I guess, of the angle. And then the y portion, T sine theta minus gravity, mg, plus normal force. So the normal force is perpendicular to the plane going up, gravity going down, mg, and then T sine theta is the y component of the tension force. And I can also use my given here that the friction force is equal to mu k n, which I already knew. So now I'm going to start solving. I'm substituting friction force for mu k n. And I also take my net y equation and solve for n, which I used to substitute back in the net x equation. And that gives me T cosine theta minus mu k times negative T sine theta plus mg equal to 0. And then I multiply both T sine theta and mg by mu k. And that gives me T cosine theta plus mu k T sine theta minus mu k mg equals 0. And then I solve for T. By first I add mu k mg to the other side, and then I divide that by mu k sine theta plus cosine theta, and then I just substitute all my values in: the coefficient for friction, weight of the cart and the boy, coefficient, g, and then I also substitute in theta, which is 26 degrees, and the sine and cosine. And that all comes out to 48.5 newtons as the tension force. And that's just the first part. And then I go on, do the work done by the woman. So I take work done by the tension force, and that's equal to T cosine theta and delta x, which I'm using it's delta r. But I'm just using delta x. And that's where delta x is equal to 120 meters. The x component of the tension force is T cosine theta, and T is equal to 48.5 newtons, which we just solved for. And I just multiply 48.5 newtons, cosine of 26, and 120 meters, and that gives me positive 5,231 joules, which would be the work done by the woman pulling the cart. So next I'm going to solve for the force on the cart due to the ground. Because the normal force is perpendicular, that one's equal to 0, so it does no work. So the work due to friction be equal to the friction force times delta x times the cosine of 180, which is the angle of the displacement. Cosine of 180 is equal to -1, so we come out with negative friction force, delta x. The friction force, we remember from the first part, is equal to t cosine theta. We got that from number 1. So work due to friction is equal to negative t cosine theta delta x. So we can substitute in those values to get negative 48.5 newtons times the cosine of 26 times 120 meters, which equals negative 5,231 joules, which you remember is actually very similar to this, except for the negative one. So now, to get total work done, we take those two values and add them together. So the work total is equal to the work done by the tension force plus the work done by the friction force, which is 5,231 joules minus 5,231 joules, which is equal to 0, total work done. Okay. Hopefully I've displayed some sort of understanding of work energy. Anyway, have a good night.